So yesterday we were here. I explained that using the mass energy balance and defining production target, you can define the required power, and then there was a discussion whether putting a margin on the production target or putting a margin on the surface to have an improvement potential from 200 to 300 kilowatt per square meter specific power rate. The specific power rate of 200 to 300 kilowatt per square meter, of course, it is a kind of empirical result of, I mean, it is the result of production. But if you read all the papers I sent you, coming from the some publications of works or publications of constructors like Demag, like Pyromet, like Hatch, you will see that these figures are really industrial figures, and they are based for dimensioning furnaces. The industrial furnaces really work like this. Okay, then we went through, we discussed the preliminary transformer rating, and Mr. Jin said, yes, but that's not enough. It's not enough to define the MVA. No, of course, it's not enough. And no, we are continuing to define not only the transformer main power figure, but also to define voltage and current to be used by the furnace. The power supply constitution of a SAF, like it's suggested here by Mr. Jean, is the same than that of an EAF. But of course, what is important is to define appropriate voltage and current. That may be different. And what are the very basics of this? First, again, to maximize the specific power rate requires to really obtain arcs, to have submerged arcs, and not only electrode immersed in slag and giving only a resistive Joule effect to the slag. The electrical features have been measured on different furnaces, and this has been done on by a research institute specialized in that. It is the Mintec in South Africa. In the past, I had a collaboration with these guys, and I in my document list, I have referenced one document giving this, where this is explained in detail. The typical arc voltage that you can obtain in ferromanganese and ferrosilicon, but also ferrochromium furnaces, are arcs of 20 to 70 volt. This is typical, and this is arc voltage measured on a ferrosilicon furnace over time. You see, of course, it may vary, but in average, it is here. It is 30 to 40, and but the fluctuation are between mostly between this is top. Mostly between 20 and 70 volt. And this is the time scale is these are hours, 4 hours, 8 hours, 12 hours. So I mean, when they did these detailed measurements, this was a real important result, because before people were always struggling, saying, you know, nobody was inside the charge to see the arcs. So this was really important to measure it, and so it has enabled also to establish the level of bath resistance, and this is about 1 to 2 milliohm, and of course the power factor you can easily observe. The power factor was 0.6 to 0.7, and I mean these features are the base then for calculating provisional voltage and current values. And this table is an estimative calculation of secondary voltage and of power for the furnace for which we made the balance. I mean, you know, for this one, we are going to define the electrical working, the electrical setting for this furnace, for this 130 square meter furnace. And what we assume is that we are going to work, the nominal current is 90 kiloamps. The size of this furnace is more or less also the size of your high metal ferromanganese furnace. You agree? It's high metal furnace is about 120 and something square meter. And this type of furnace has electrodes like, I think I indicated it, yes, electrode diameter of 1.6, 1.7, the pitch circle is 4.5 to 5 meters, and through such electrodes you can easily use 100 kiloamps.
One question. This power factor F is minus. What's minimum minus?
Well,
What's
sorry.
minimum? Minus. F. Power factor F plus.
Power factor? No, this is not minus. This is just saying that the unit, there is no unit. It's a pure number. You understand? This is the sign. Normally you have volt or amperes or meter or square meter, and here it's no unit,
No.
pure number. That's the meaning. It's not minus. Pure number. Okay, how to set typical values in case of 90 kiloohms? In case of 90 kiloohms, this, you made a picture, this is okay, I can... Okay, what we're doing now is very approximative because we all know that in an arc furnace the relation from the real electrical relations are include reactance, and so we should calculate real impedances with resistive part and reactive part. We simplify the problem in saying we will add, to calculate a voltage, we will add an arc voltage plus a bus resistance times the current. Of course, I know, actually we should do this in vectors, using impedance. But let's to explain how it works. Here, in this case, we have 90 kiloohms. And you remember we had arc voltage from 20 to 70 volt. If we work in the range then these most industrial furnaces work. And then we have bus resistance from 1 to 2 milliohm. So we have 1 to 2 milliohm times intensity of 90 kiloohms. So the result of that is 90 to 180 volt. No. It's okay? Yes, it's okay. Do you agree?
Yeah.
Huh? And now, if we assume that there is no important reactive part, we add these two, and you see we have the result of that is we are between 110 and 250 volt. It is here. And what is the power associated? Then if I take this total voltage, the power is 1.73. This is root of 3. U, I, and power factor. Let's calculate. cosinus phi is power factor. Let's take the higher value, 250. Let's take power factor of 0.7. Can you calculate, somebody?
$27,247.
247. No.
Right.
27. Okay, about 27. Yes. Okay. So you see, here we have 27. That's for here, and then I imagine two cases: the real maximum case where we had 120 kiloamps. 120 kiloamps would require electrodes of 1.75 or 1.8 meter, but it's possible. Maybe you remember where? Oh no, sorry. Where are the examples? I showed you. Here. This big furnace. These guys were working with, I think, with I should find it out, with 130 kiloamps. 130 kiloamps. And you see, their secondary voltage was 220. So it was fully in the range we had. And also high metal is 150. You see, high metal, they are in the lower range with 90 kiloamps. High metal is working with 90 kiloamps. Where is 90? Here. So let's do it for 120. So for 120 we have, I made the same exercise. We have 20 to 70 volt plus so this is 120 and 240, 70 plus 240. Yes. And if you calculate then the power for the highest 310 volt, you find out 37 milliwatt. You see, and then dividing by the surface, here we are roughly a bit lower of 300 kilowatt per square meter, and here we are roughly at 200. And so you see, just departing from the electrical capabilities and from the electrical basics, we find out again the level of specific surface power that we used. It's all coherent. It's coherent. Again, what I don't know if I am clear. I'm saying the following. We do mass energy balance. We find out the power, and then we say from using the specific power rate range, we define a surface. This is what we did yesterday. Yeah? And now this is then 13 or no 13. And this is electrodes. And what I say no is different. Having this furnace dimension and departing with these electrodes, I'm able to have 90 kiloamps up to 120 max. I will have, working with ferromanganese, ferronickel, etc., I will have arc voltage of 20 to 70. I will have bus resistance of 1 to 2 million. Using this, I find out some 27 to 37 megawatt. You see, it's just to say it is coherent. The two approaches are different. And so, this is confirmed.
결국적으로 찾아가는 거예요, 저렇게. 저 보면.
그렇지. 그게 저 0.2, 0.3 저게 중요한데, 저게 사실 한계가 지금 1.5배 차이잖아. 크거든. 그러니까 저걸 어떻게 적절히 찾느냐가 중요한 것 같은데, 그거는 뭐 경험이라니까 그게 문제네.
And I can tell you that these guys, they told me that when the electrodes are new on this very big furnace, when the electrodes are new, they have a resistance slightly below 1. But the electrodes are not new because they are self-baking electrodes. But when they are in good shape, the shape of the electrode you see when you extract it, you see when the shape is like this, that is good shape. Okay. And they told me that when the electrode self-baking does not work well, it's something like this. I'm not a specialist of the electrodes. And then this is increasing. The resistance is increasing up to more than 2.5. Okay. But at the same moment, when you have this, you have less arc voltage, because you understand that these are not good conditions. If you have coke here, it's not good conditions to form arcs. This is good. This is good. This is not good at all. So, in this case, you have a higher resistance. So the second term, this term is increased, but this term is 0. So there is a kind of self-balancing effect.
Do you include self-making and electrode lifting and lifting system
In the presentation?
No project.
No.
This
Here,
way.
you mean here. Okay, yes, you're right. This one.
And hot cooking.
Okay, so you see, these things are more or less well known. It's just that there are limitations given by experience. And nevertheless, the target is to work like this. And then working like this, meaning having good arcs, and at the same time being able to work with the highest currents, enables you to have high voltage, or even 300, from 250 up to 300 volt, and then to have the highest specific power.
What about the base resistance 1 to 2? It is always applied the same, isn't it? Can be different from the condition of O. No?
It can be different, of course. For you know, in the publication you will see this. Sorry. This was measured for ferrosilicon furnace, but I know that for ferromanganese it's the same.
Same?
Yes.
ferromangan, ferrosilicon.
What I have heard from for ferronickel, it's you may have this also, but it's more difficult for the reason to have all. It's more difficult to have always an arc voltage like this, for the reason that you have much less coke. Meaning you have the problem that you don't have everywhere coke floating. Because you put, instead of putting per ton of ore, instead of adding, you remember, 150 kilo
Then
coke?
it can be decided not by ore, but by coal, you mean? Coke.
By coke. Because you see, you need the hot, coke is giving hot spots
I see.
to stick the arc on.
I see.
And therefore, the largest ferronickel furnaces, actually, they put the very biggest electrodes over 2 meters, I think, and they increased the current because the voltage was not so easy to guarantee due to that. But of course, we will see in the balance of ferronickel. It depends also. You may have instead of having 25 kilo coke, as I showed you, you may have in some cases. Here we have 25 kilo coke. In some cases, you may have the double, which is better condition. But this is very few. This is very few. So in this case, what would I say to the electricians that are defining the transformer? I would say, you see, I would say to foresee as base this working point, but as a maximum case this one, and maybe for periods where for any reason you would decrease the current, this level. But I think this definition should be enough for people making the transformer. I cannot define the details of transformer, but I would say we must be able to work like this, and like this. So your voltage steps must be from roughly from 100 to 300. And so you can decide if you have 10 steps, you can decide it's by 20 volts. Of course, on a smaller furnace, this is all much smaller, as I give you in the short note. On the pilot is much different. It's much smaller in a way.
Because in PowerPoint we cannot define this resistance, but we expected PowerPoint resistance is under the 1 milliohm, we think.
You think under 1 milliohm?
Yeah, under the 1 milliohm.
This is experience from these guys from the large ferromanganese furnace. They have about 1 milliohm, but they have more when the electrode is in bad shape. And you say high metal, they told you smaller than 1 milliohm?
또는 어차피 그거니까 그렇지. 코킹한 게 아니라 공장에서 만들어 온 거잖아. 달라지니까 그거 훨씬 좋겠지.
그러니까요. 카본 일렉트로드 들어있다라고.
that is not cooking not electrode. That is for the EAF or leather furnace. They are machining the side.
It's a graphite electrode.
Graphite electrode.
Yeah.
So I
okay,
think it's
graphite.
better than.
Okay, graphite electrode should be even better than this. Yes, you're right. Huh? Possible. Yes. So it's possible. Yes.
If we want to increase production, and accordingly we can increase the power input, right? Then that intensity will be increased more than 0.3 or 0.5.
No. This is corresponding to this, and this is already.
I mean,
This.
if we increase the power input
More than this one.
more than
No.
that one, the 0.3 megawatt per
Yes.
square meter,
And
what happened?
explain me how you increase it.
그 TL 용량 때문에 올리고.
You must give me a set point. How do you increase it? Do you have? How do you make higher voltage? Or you know there are bigger furnaces. There are for round furnaces. 40 megawatt is around the maximum that exists. Not EAF, SAF. Huh? For round furnaces, you will hardly find furnaces. Look. No, it's 50 megawatt. But using 130 or 140 kiloamps. Very high current. Huh? But on a round furnace with 3 electrodes, it's difficult to go over this. Then you may have furnaces with higher power, but these are the furnaces, the long ones.
몰랐어?
모르죠.
저렇게 많이 당한 편이에요.
But I will not recommend that.
해치.
Yes. Okay, I mentioned it later on in my presentation. It's possible.
결국 저게 원료로 가는 전력량이 딱 정해져 한정이
아니
있습니다.
TR에서 할 수 있는 그게 아니고 TR이 지금 현재 기술로서
예.
전류를 낼 수 있는 한계가 있단 말이야. 그 이상 대전류를 흘려주는 거잖아 SAF는.
I think
그 때문에 DL은 못하는 거지. 많은 전류 흘려줄 수 있으면 아니 그게 리본 묻잖아. 어떻게 전류 흘려줄 거냐고. 응?
This type.
예.
그걸 묻는 거야.
For me, I'm not a specialist. I don't know. I cannot define a furnace like this because there are many difficulties in the design. Because a round furnace has a round shell, round refractories. Everything is symmetrical. But here you have problems. At all corners. Here you have corners. Not easy to handle. Okay, it exists.
전류를 못 높이면 전압을 높이면 어떻게 됩니까? 그러면
그럼
아크가 생기기 때문에 안 되는 거죠.
아니 생기는 떠나서 전류 저항으로 하니까 전류를 많이 흘려줘야 되는데 저항을
그래서
높여요.
그런 거죠.
좀 이상한 생각
그래서
시작했어.
물어본 거라 지금 원료하고 관계가 있어 그렇구나.
원료가 관계가 아니고 전기에서 보내준다니까.
전기에서 보내주고 싶어도 원료 쪽에서도 못 받아줘요. 결국 원료 특성 때문에 그렇게 맞춰간 거 아닌가요?
아니 진짜 아니라 그러는데 자꾸 그러고 있어.
아닌가요?
어차피 아까 전압을 높인다는 게 아크 전압.
예. 그게 한계가
2차
있잖아요.
전압을 높이는 거잖아요. 2차 전압을 만약 높였어. 전압을 300으로 바꿨어. 거기에 전류가 이제 한계가 있는 거죠.
TR에서 보내주는 전류의
전류가
맥스가
한계가
현실적으로 한계치가 있기 때문에
예.
SAF가 뭐 45MV나 맥스 한 60MV까지 나왔는지 모르겠네. 그 정도 TR에서 한계가 있단 말이야. 그러니까 아까 네 묻고 하는 질문이 어떻게 전류를 보내줄 건데 물어보잖아.
그렇게 물어보고.
그러니까
그게 그
전류를
이유란 말이야.
저기서 전류를 한 개짜리를 2개, 3개로 만들면 이제 전극을 3개 아니고 6개를 만들면
TR을 많이 써서 하자는 얘기인데.
그치.
지금도 TR이 한 개로 하는 게 아니라 그 일렉트로드 하나하나에 TR을 다
하나에
달아주잖아. 그래서 크게 한단 말이야. 응?
상당
그 얘기는 내가 알겠다니까요.
그러니까
아는데.
그거라니까. 원료에서 못 받아들일 수가
그러니까.
있나? 원료에서는 당연히 받으면 지가 받은 만큼 빨리 녹아버리잖아. 어? 그 다음에 빨리 들어 생산성이 증가되지. 원료에서 뭘 못 받긴 못 받아.
아니 원료에서도 지금 저기 뭐냐 리지스턴트도 그렇고 아크 볼티지도 한계가 있는 거 아닌가요? 같이.
아니
전달 매질이
지가-
전달체가 아니니까.
지가 한 개 넘으면 어떻게 녹잖아. 스크랩도 뭐 한 개 없나? 스크랩도 380kW 해가지고 있잖아. 그거 녹아버리잖아. 녹아버리고 나면 그 다음 노래 생산성이 오히려 증가되지. 그래서 우리가 저 TR을 용량을 키우는 거 아니야. 근데 이거는 TR 용량을 키우는 한계가 있단 말이야.
오케이.
So, if I would summarize, this shows that the right way for me to dimension the furnace is to define the nominal power. You remember? This was the nominal power for 10 ton per hour furnace. And but then to define the surface using 0.2 megawatt per square meter, and this is giving this furnace. And then having this, you define the electrics, of course, to obtain at least this power, but you can define the transformer to obtain a higher power. Then you will be able to work at 0.3 at the highest, at the record level. Electrode regulation. Do you need that I speak of electrode regulation, or I think it's the same principle than for EAF?
It's different, I think. Same?
The principle is same,
Principle is the same.
but you know, there is a big difference. There are two different big differences. The first big difference is the weight of the mechanical of the electrode. It's much bigger.
Bigger, yeah.
That's a big difference, of course. But this big difference is compensated by the fact that the speed, the variation speed, is much smaller. Is much smaller. But then I'm not a specialist of this, but the basics are the same.
The ERS is the same as the EAF.
Yes. Same principle. But of course,
Can you use the same software of the?
I would say yes. Yes. Then I would recommend to make some simulation and to compare with that of high metal. I would recommend to, you know, because they have one, so it's good to compare because what is different, as I told you, what is different are the constants of the regulator of this. Here, this one, the constant of the reaction will be different because the weights are different and because the speed at which we want to react,
It's different.
the speed is much different. But the basic principle is the same.
Mm.
It is based on measuring,
Mm.
on measuring,
Mm.
on measuring the height, on measuring the currents, and reacting from time to time to adjust
Mm.
either the voltage or the impedance.
How to lifting down? How to lift down of the
This
this
is-
electrode?
This is fully. These are this is only hydraulics. How do you say piston?
Yeah, piston cylinder.
Cylinder. Yes.
Mm.
You know French.
And but how to can you explain the mechanism of the electrode down, and the upper side is low material coke, yeah?
Yes.
And cooking and
You charge.
Mm.
You charge at a very high point.
Yeah.
It's a very long envelope,
Yeah.
a very long pipe of steel,
Mm.
and
Piping down, and
I.
cooking continuously.
It descends, and
Yeah, I would like the mechanic mechanism. Yeah.
the mechanic.
Yeah,
The
and
mechanics.
I know it's a electrode that has a big thin plate, round plate.
And,
Yeah.
and,
And
and,
then-
you weld a new plate
Mm.
after you see. Here.
Yeah.
And this part is already hot,
Mm.
and this is here your steel has already disappeared because it's too hot, and but at the top you charge material, and then it descends. It's this is what do you
Begin-
say,
Perhaps.
clamp.
clamps,
Yeah.
and then again after when it's worn, like for graphite electrodes,
Mhm.
you hold it and you open
Yeah.
and you let it descend, and after you let it descend, you will weld a new pipe here to compensate the wear here,
But
and you feel.
when you open the clamp, the electrode.
No. You actually you have two systems. You open the one,
Mm.
the other descends, and you
Clamp.
clamp and you go up.
Mm.
Cool.
Okay, I'm not a specialist of this mechanics.
잡아주는 게
but,
하나
아니,
아래로 왔다 갔다
그걸
하는
알겠는데
거구나.
정확하게가 좀 헷갈리더라고.
but this is rather it's a rather simple principle, but it's huge mechanics because of the big weight.
이렇게 지금 파란 실린더가 이거 쫙 내리면 딱 내리는 밑에 그 실린더가 녹색 실린더 가운데 있는 게 내려온 상태에서 거기서 클램핑을 하면 파란색 실린더 다 내려야 되나? 내리고 그런데 파란색 실린더를 내리고 그 다음에 위에 녹색 실린더를 쭉 펴서 위로 올린 다음에 잡고 다시 파란색 실린더 올리고 이렇게 되겠네 자체가.
Here you have a double.
두 개.
네, 맞네.
You have a double clamping system.
음.
You have a double system. You must have a double system.
I guess it's like this. Yeah. It's the first lifting down the whole part, lifting down electrode,
Yeah.
and stop it, and lift up just one
Exactly.
clamp, and open the bulb. 그래 되겠네. 아니, 그지? 그래 되겠네. 메커니즘이 난 요 두 개만 가지고 이 두 개만 가지고 하면 떨어지게 돼 있거든. 인간이 이해된다.
양쪽 옆에 있는 게 실린더 아닌가요?
요거 실린더 두 개, 여기 실린더 두 개.
고개 실린더. 예.
그러니까 지금 메커니즘을 보면 어떻게 되냐면 이거 전체가 일단 내려오는 거지. 요 두 개 다. 그럼 요 전국 내려오잖아. 내려오고 나면 딱 정지했다 이거지.
이것도 안 그러겠는데.
정지하고 그다음에 이걸 이해하면
자꾸 끌어올리는
일단
거예요.
잡았잖아. 정지했다. 이걸 위로 올리는 거지. 요거만 이렇게 올렸다 딱 잡은 상태에서 얘 이 실린더하고 이 실린더 동시에 쫙 올려서 이거 클램프 풀려 있지 밑에는 위엔 잡고 쫙 올려서 위에 가 있고 이렇게 움직이겠네 자체가.
딱 잡은 거 딱 풀어주고 요 놈이 잡은 상태에서 탁 내려오는 거죠. 실린더니까.
그런 거 돼 있어.
내려왔다가 다시 얘 꼭 잡으면 다시 올라가고 다시 잡고.
그런 것도 있어.
내가 왔다 갔다.
이게 세네 개 시스템이
그래
있어.
보이네.
세 개 시스템.
모르겠어요. 나중에 더 봐야지.
Just guess. 세 가지 시스템이 있거든.
Okay.
그래요.
I think you
어.
you know it better than me. I know
Okay.
not the details.
쿠킹을 어떻게 잘 할 거냐, 쿠킹 용량 조절하고 이런 게 중요하겠네.
Okay, this is just a picture. I think it was of a ferronickel furnace, showing that in ferronickel, if the charge is hot, it is a certain height.
Okay, just check.
These are the examples we already commented.
Yeah,
This was a. And now we continue, and really the key parts for having a sturdy furnace working on long campaigns without stoppage, without failure, is the important parts are, of course, what we just discussed, the electrode supporting and regulation. It is the refractory lining. It is, of course, the material charging. It is the wall cooling of the vessel and the metal tank. These are the key parts that must be well designed. Okay, I will comment only the refractory and the wall cooling, because material charging, I'm not a specialist of this part, because I would say it's pure mechanic. What is not mechanics is to define where to charge. And I told you that on a large furnace, you may have 9 or 12 or 15 charging points. This is a lot. This is a lot. And my experience in that field is that on a small size furnace, it was roughly a bit more than 4 meters diameter. Even there, they had, I guess, 5 charging points, or 4 charging points, or 6, 4 or 6. They had, actually, in this case, it was not the point of charging that was it was well designed, but if you have a small furnace, you cannot have everything too close, and the pipes come like this, and the reason of failure or of bad functioning of the distribution of material, the reason was the wear of the pipes. The pipes were corroded and destroyed, and so the material went out before it should. And at that time we defined new steel grade to withstand the higher temperatures and corrosion for this small furnace. And afterwards it worked perfectly. Okay, so let's discuss. This is a picture of RHA, which is you may know, it's the largest refractory supplier, I guess, worldwide. It is the former Didier, German company. Didier Radex merging all together. Today, RHI. Here, it's a nice picture of an SAF, and this is of an SAF, for instance, for ferromanganese. Could be. Can be also for ferronickel. What you see is that actually fundamentally there are 4 family of bricks plus 1 derivative. The 4 family of bricks that can be used are the magnesia bricks, MgO, the magnesia bricks fused, because the normal bricks, most of the magnesia bricks are sintered. Then you can have the bricks fused. I will explain afterwards. Then you have the magnesia bricks sintered or fused, but tar impregnated. You have the aluminum bricks, which are normally used for the upper parts, which are not so corroded, and you may have magnesia chromium bricks. This means MgO, Cr2O3. You know how magnesia bricks are fabricated. You crush magnesia rock, MgO rock. You pre-heat the crushed material. Then you sort it. You recrush it when you have very fine material. You press it, and you can press it with different additives, with different binders. You have resin binders, you have other binders, spinel binders, and you press it in a press to give the form of the brick, and afterwards, these are the sintered brick. Afterwards, these bricks are passing through a heat treatment furnace to be cooked and to be baked at a very high temperature, at something like 1800 degrees C or 1900 degrees C. These are the sintered bricks. And the fused bricks, as you can guess, fused bricks means that you go through a very special SAF furnace working at 2100 degrees or so, and you melt the magnesia, and afterwards you tap and you cast, and the brick and the fused bricks are then from material that has been melted. Of course, they are very resistant, but these are the most expensive as well. So for a ferromanganese furnace, basically, I would recommend this. And today, with the progress made by high-density MgO bricks, I'm confident that this holds for a long campaign. In some cases, I give you an example. This was on a small furnace. This is a real-life example. This is interesting because this was an old design, and you see in an old design you have a kind of how do you say concave. The bottom is not. Excuse me. In the old design, the bottom was not like this, it was like this. I exaggerate. You see? Because the bricks characteristics were not so good that they could expand, and this gives you a direction for expanding. Today it's no more required, and you can see here. I don't know. I cannot see. I think, of course, it's difficult to see details, but I think there is no more. Today, there is. They never make on new furnaces this. How do you say? Round bottom. Here you have it. Even on a small furnace, because this was a kind of 5-meter furnace. So this is the steel shell. You can see the four. These are the so-called skew bricks. These are magnesia chrome bricks. Magnesia chrome. And this also, I guess, yes, magnesia chrome bricks. And below the magnesia chrome bricks, there is a layer of graphite blocks. The objective here was to not be too insulating and to not freeze the bottom of the bath, because if you have an insulating material, no, it's the contrary. If you have graphite blocks, and here you see this is the arrow means that you have circulating air. This is going to organize that you have a small solid shell